To get at the idea of looking at the magnitude and phase of a transfer function, we can start first with convolution. Convolution gives us that y of t is equal to the transfer function, the differential equation convolved with the input to the system. And this is simply the integral from minus infinity to infinity of h of tau times u of t minus tau integrated over tau. And we saw that from one of the theorems that this is equal to the Laplace transform of h times the Laplace of u. And this idea is that y of t is the solution to the differential equation h of t, so that's some differential operator, which is being forced by some input u of t. So, for example, h of t might be, say, y dot plus ky, and that would be equal to u of t. If we go ahead and look at this integral down here, and we let u of t equal e to the st, then where s is some complex number, all right, and that would be a valid input. And if we have complex conjugates, we can get sines and cosines. Then we end up with y of t is equal to the integral from minus infinity to infinity of h of tau e to the s t minus tau d tau. And I can go ahead and actually I can pull this e to the st apart, factor out the e to the st, because that is not part of what's being integrated. So this is h of tau times e to the st times e to the minus s tau d tau. And that's got to be equal to the integral from minus infinity to infinity of h of tau, then times e to the minus s tau d tau, all times e to the st. But notice this thing here is just the Laplace of h of t, or h of s. So what we find is that y of t is the Laplace of the differential equation, h of s, times the input e to the st. So if we go ahead and let s equal j omega, some complex number, and we then say, let's let u1 of s equal e to the st over 2 equals e to the j omega t over 2, then y1 would be of t would be h of j omega times e to the j omega t all over 2. And likewise, if we let s equals minus j omega, then u2 of s equals u2 of j omega, minus sign, equals e to the minus j omega t over 2. And therefore, y2 of t would be h of minus j omega times e to the minus j omega t all over 2. And finally, y of t would equal y1 of t plus y2 of t if u of t were equal to u1 of t plus u2 of t. And this is all from superposition. Therefore, our final expression for y would be h of j omega e to the j omega t over 2 plus h minus j omega, h of minus j omega, e to the minus j omega t over 2. So in general, h is a complex function, or say it's a function of a complex number, and when we evaluate it, h will have a magnitude and phase associated with it, and we could write that down in polar form. We could say that h of j omega is equal to whatever the magnitude of the function is, which is only going to be a function of omega because the magnitude has to be a positive real number, times the exponential of j phi, which is a function of omega. And we could also write that h of minus j omega would have the same magnitude, because it's just the negative, and it's symmetric in the real axis, times e to the minus j of phi of omega, where in general, m of omega is the square root of the real part of h of j omega squared plus the imaginary part of h of j omega squared. That's just the standard complex way of looking at complex numbers. And phi is the inverse tangent of the imaginary part of h of j omega all over the real part of h of j omega. So using these relationships in there, we can plug that into the equation for y of t, and we end up with y of t is equal to m of omega times e of j phi of omega times e to the j omega t over 2 plus e to the minus j omega, phi of omega times e to the j omega t over 2. That's all over 2. And we can go ahead and look at these terms here, and notice I can add these together. Sorry, there should be a minus sign there. We can add these together and do some work to factor things out, and we end up with m of omega times e of j times omega t plus phi of omega plus e to the minus j times omega t plus phi of omega. And that's all, all over 2. Let me create a new page here. And we can use Euler's formula, which says that e to the j theta is equal to cosine theta plus j sine theta, and therefore e to the minus j theta is cosine theta minus j sine theta. And if I add these together, I get I get e to the j theta plus e to the minus j theta is equal to 2 cosine theta. So cosine theta is equal to e to the j theta plus e to the minus j theta all over 2, which is exactly what we had, where theta here is equal to omega t plus phi of omega. So using that relationship, I now have that y of t is equal to m of omega times the cosine of omega t plus phi of omega. And notice in this case, from using these relationships, where the input u is the sum of these some exponentials, you go back and look at that, the total input was actually e of j omega t plus e to the minus j omega t all over 2, which is just cosine of omega t. So we can look at the magnitude and phase difference between y and u, where so the magnitude of y of t is just m of omega, which is the magnitude of h of j omega, and the magnitude of u of t is just 1. And notice the phase difference, so this is on the magnitude side. Notice the phase difference between the input u of t, which is cosine omega t, and the output cosine omega t plus phi of omega is just that angle phi of omega, which is simply the inverse tangent of the imaginary part of h of j omega over the real part of h of j omega. So what's interesting about this is that I can tell you the magnitude of the output relative to the magnitude of the input and the phase difference between the output and the input of this dynamic system only by knowing what's going on with the transfer function, not necessarily the exact input, which shares cosine omega t, and exactly what the solution of the output is. I can just look at the transfer function evaluated at j omega and take its magnitude, and the transfer function evaluated at j omega and look at its phase angle.